the lights here a bit. So last time we looked at this figure. Just turn this one on. We looked at this figure here, and we divided it into two just to get it a bit easier to see. And we saw that we had something called a subsea stuffing box up top there. And I couldn't really answer what it was. But now I've checked it out, and now I've figured out what it is. And they are doing the wireline service down through here, which means that they are moving a wire through everything here. So the stuffing box is actually ensuring that the pressure from the well doesn't escape past the wireline as it's moving through here. So it's basically sealing along this wire which is moving up and down. So that was the whole part with the stuffing box. We'll just jump forward a bit to where we were. Past the different protective structures, the flow lines. And we started looking at the wireline equipment. And we saw this one. And we were supposed to see this fracking one, but we didn't have sound, so we're going to do this one now. So I'm just going to check that the sound is on here. Looks that way.
What is hydraulic fracturing, or fracking?
And I have to jump to...
Since the Industrial Revolution, our energy consumption has risen. Has been known since the 1940s. Nonetheless, only in the last 10 years has there been quite a fracking boom, especially in the USA. This is because most conventional natural gas sources in America and on the European continent have been exhausted. Thus, prices for natural gas and other fuels are rising steadily. Significantly more complicated and expensive methods, like fracking, have now become attractive and profitable. In the meantime, fracking has already been used more than 1 million times in the USA alone. Over 60% of all new oil and gas wells are drilled by using fracking. Now, let's take a look at how fracking actually works. First, a shaft is drilled several hundred meters into the earth. From there, a horizontal hole is drilled into the gas-bearing layer of rock. Next, the fracking fluid is pumped into the ground using high-performance pumps. On average, the fluid consists of 8 million liters of water, which amounts to about the daily consumption of 65,000 people, plus several thousand tons of sand and about 200,000 liters of chemicals. The mixture penetrates into the rock layer and produces innumerable tiny cracks. The sand prevents the cracks from closing again. The chemicals perform various tasks. Among other things, they compress the water, kill off bacteria, or dissolve minerals. Next, the majority of the fracking fluid is pumped out again. And now the natural gas can be recovered. As soon as the gas source is exhausted, the drill hole is sealed. As a rule, the fracking fluid is pumped back into deep underground layers and sealed in there. However, fracking is also associated with several considerable risks. The primary risk consists in the contamination.
So that's how they do the fracking stuff. This one also looks at the problems associated with fracking, what it can, the sort of hazards it can lead to for the people that live close by. But you'll be able to watch it on your own once this one is released, when we're done with Appendix A. The point was just to show that there's a lot of things that we can do down the well hole, apart from just exchanging safety valves and stuff. There's a lot of stuff they can do far down into the well and send the equipment down to do a lot of work. So we looked at started looking at the through flow line method last time, where we send equipment all the way from the rig through the flow lines, and then we divert it into these loops so that it can loop around and then go into the well. And this means that we don't have to have a vessel situated directly above the well that lowers this wireline equipment down into the well. So it's fairly, if you have the equipment for a through flow line operation, that's a lot cheaper than doing a wireline operation. But setting up the equipment for a through flow line operation in the first place, that's more expensive than doing wireline operations. So this is sort of a decision that has to be done while they are planning the field. Are they going to go for through flow line option, or are they going to go for the wireline option? So we see a bit closer in for basically this part here. So we see it with a bit more detail. So we have the flow lines coming in here. They go into these loops, and then we send it down into the well. So as you can see, the flow lines go pretty far down past the surface-controlled surface safety valve, and that's one of the tasks of these through flow line equipment, is to exchange different valves down here and stuff. We'll look a bit at the diverters that can be used. So we have one diverter which is non-selective, and here you can actually end up moving into both of them, but you see there's a slightly smaller cross-section here, so the equipment won't pass into this part of the line. It will be diverted. You also have the sort of a paddle that lies in front of it that you can have. So when you have a flow coming through the line this way, it will just flow straight past. But if you're sending flow line equipment down, it will hit the paddle and be diverted into there. And you also have paddle diverters, which are selective, where you can actually operate it to the paddle to either move so that it's blocking off here or block off there. So there are a couple of different designs there. And usually the equipment looks something like this. You have loads of different units that are linked together, basically in order so that they can manage to do the curvatures of the loops and whatever else might be found along the flow line of curves. And you have the piston units in the start. You have a stem, the hydraulic stuff, and then the pulling tool, which is the back of the tool, which you use to get it back to the rig. So now we're going to start looking at control systems. So the control systems for different subsea valves, mostly you control the valves through the control systems, and usually you have different sets of control systems. So you might have one control system if you're going to do some maintenance work down on the well, and then you have another control system if you're doing regular production and stuff. But mostly it's like this. We have the water line here, and then we have topside equipment, either on the floating vessel or on the rig. So you need a hydraulic unit. So you have a hydraulic unit there. You have different control panels up here. If the system is really old, that might just be more of a hydraulic panel, so you have actual hydraulic valves that you are operating on a big panel. But mostly nowadays they use electronics to control the hydraulics. And all of this is connected down to the Christmas trees down by the wells. So in this case we have 2 Christmas trees on 2 wells. And here you can also see a drilling rig unit where it has the hose reel where it's lowering stuff down, and it has its own control panel and everything there. So there's a lot of different different categories of control systems. So we have the direct hydraulic control systems, where you have a control panel topside, and then you have a single hydraulic line down to every single thing that's going to be operated on the subsea tree. Every valve has its own direct connection through the hydraulics, which is fair enough. It can be, let's just avoid this one. It can be workable for up to 4,000 meters. So you can have 4 kilometers of hydraulic hose between the control panel and the subsea valves. But one thing one has to think about is that the further apart these are, the longer it will take when you start manipulating the controls up here, the longer it will take before the valves on the subsea tree reacts. So it might actually take quite a while before it reacts. So this isn't something where you can just turn off a valve and then you have stopped the entire flow from the well. It will take some time before things starts to happen. Then the next one is the piloted hydraulic one, where we have connections down to pilot valves, and then you have this is sort of the main line, which is delivering the main part of the pressure, and then you have the controls going to pilot valves, and then this part distributes everything to the correct valves. So it distributes from the main line and then into the different valves. So you get a bit more of a quicker response when you're using these pilot operated ones, but these are also around 4 to 5 kilometers is basically the maximum length for it. The next one is sequenced hydraulic. This basically means that you are using different pressures. So you have a set of valves that are controlling the subsea tree valves, the Christmas tree valves. So you have a main line delivering the main pressure, and then you have a sequence supply. And the sequence supply works that, for an example, the example they have in the appendix is that it works on every 30 bars. So if you want a certain operation to be done down on the Christmas tree, you will raise the pressure in the sequence supply to 30 bars. Then something will start happening. It will activate one of the valves down on the Christmas tree. Then if you want the next operation to be done, you increase the pressure with another 30 bars. So now you're up to 60 bars. Now something else will be activated. Another valve will be activated on the Christmas tree, and so forth and so on. And you can also sort of skip steps so that you can jump directly to 120 bars if that's the sequence that you need for it to do the operation that you intend to do. So this is another way of sort of controlling it. Instead of having direct control over all of the smaller pilot valves, you just use a valve system which is sort of pressure-based. Then we have the electronics, wasn't it? Electro-Hydraulics was the name for it. And for the electro-hydraulics, you basically have valves down here that are still doing the work, just like in the pilot valves and the sequence valves. They are doing the work of directing the main supply down to the correct valves in the Christmas tree. But now, instead of controlling them by hydraulics alone, you also have electronics. So you're sending electronic signals down there to electrically operated valves to do stuff. And then you have the multiplex systems, which is sort of more similar to what we would expect from the kind of automation that we are used to in our regular lives right now. These are old systems, but this is what we would expect now with computers running most things and everything. We would have one single line coming down here, which are sending the control signals. This one will process the control signals, and it will feed the hydraulic pressure supply into the correct valves in the template. And here you can have this one multiplex system can control all of the wells in an entire template. It's not one specific well. So you can see you are basically saving a lot of cables going up and down if you can use a multiplex system. So we'll look a bit more closely on some of these. So the direct hydraulic system is, of course, connected. You have the manual valves up top, where you can open and close them. Everything is connected directly to the equivalent valve down on the Christmas tree. So you have to have a whole lot of hydraulic lines going through the umbilical, which of course makes the umbilical fairly thick and heavy, and it becomes quite expensive to create these systems. Then we have the the piloted hydraulics, where you have the control panel up top. You have the umbilical with loads of hoses going through it. However, you only have one large hydraulic hose going down, which is the source, which is delivering the main pressure supply, while the other ones can be fairly small, because they don't really need to deliver all that much fluid down here. They only need to deliver a tiny amount of fluid, so they just need to keep the pressure up along the line. So the lines don't need to be really thick here, because then you go down to the pilot valve. You activate the pilot valve, and it will let pressure from the pressure supply be sent into the actual valve that is going to be operated. Then it's the sequence one, where we have the pressure regulator. So we regulate the pressure to the correct amount. 30, as it said in the appendix, might be other sequences that are used. And for each pressure increase we do, we are activating more and more stuff down here. So it will, as we increase pressure, we will start activating more and more of the valves down here. Then it's the electrical hydraulic. So we have the open-close functions electrically here. They go down. Then you suddenly don't need a hydraulic hose anymore. You just need a power cable to send a signal down here. That's even thinner than the pilot hoses for the hydraulic systems. So you save even more space in your umbilical. You still have the main pressure supply coming down and being directed through these electrically controlled valves. And here we actually have a system to show also with the electro-hydraulic.
As our industry continues its commitment to procure oil and gas from around the world in safe and environmentally sensitive ways, Halliburton is proud to introduce its electro-hydraulic control system, the -EH. By incorporating the latest advances in design and technology, the Halliburton -EH provides operators with the comprehensive subsea well control that's needed in the highly demanding and regulated deep water environment. Poor environmental conditions and emergency situations can require an operator to shut in and disconnect from a subsea well. In this challenging situation, where risk increases exponentially, time is of the essence and reliability is key. The -EH control system is a key safety technology designed to work in conjunction with Vito, Halliburton's premier 15,000 PSI subsea safety system. -EH provides a rapid dual barrier well shut-in and landing string disconnect with no excess complexity. Unlike conventional control modules that use complicated electrical and hydraulic systems to deliver pressure to their tool functions, the -EH system utilizes smart, redundant electronic controls to perform the emergency well shut-in and landing string disconnect in less than 15 seconds. The -EH module is a passive system during normal operations with full direct hydraulic control and full integration with Halliburton's ResConnect acoustic well testing system. The system is rated to 15,000 psi, 350 degrees Fahrenheit, and 8,500 psi marine riser hydrostatic pressure. It has achieved API and DNV qualifications. Halliburton's -EH module with Vito consists of a 15,000 psi surface and downhole control system, a retainer valve, a subsea safety tree, a lubricator valve, and a quick union. This premier system offers an effective barrier for the environment and personnel on board semi-submersible or dynamically positioned vessels during exploration and appraisal well testing. The system's modular design means you can create a custom solution that's just right for your application. No matter where you need the Halliburton subsea safety system, it can be configured to your specific well isolation needs. Once the emergency quick disconnect is initiated from surface, the -EH system will function the tools in less than 15 seconds, which can be seen on a customizable software screen, giving real-time data display. The first function is closing the lower and upper ball valves. The lower ball is designed specifically to cut wire line, slick line, and coil tubing up to 1 3/4 inch, and closure of the upper ball will facilitate the safe containment of the well. In the next stage of the disconnect sequence, the retainer valve ball closes, automatically opening the vent sleeve, which vents pressure between the subsea safety tree and retainer valve. This closing of the system's ball valves means that with Halliburton's Vito safety system, not only can the well be isolated, but also the contents of the riser string will be contained from the environment. The prior sequence of closing the subsea safety tree and fully functioning the retainer valve allows the landing string to disconnect at the latch mechanism incorporated as part of the subsea test tree. The rig can now disconnect the lower marine riser package from the blowout preventer, allowing the rig to move off location if required. Once the emergency has subsided, the rig repositions over the wellhead and the lower marine riser package reconnects with the blowout preventer. During reconnect of the landing string, the system safety tree has a passive orientating latch, so realignment of the tree's hydraulic safety functions is easy. There's no need to manually rotate the landing string to achieve engagement. At this point, pressure integrity can be verified, and the -EH and Vito systems are ready to recommence operations without retrieval back to surface. Safety and simplicity are paramount in deepwater well testing. The -EH system delivers both. -EH only utilizes electro-hydraulics to provide rapid dual barrier well shut-in and landing string disconnect in less than 15 seconds. What can you do in under 15 seconds? To learn more about Halliburton's -EH and other subsea solutions, please contact Halliburton.
So that was a quick introduction to one of Halliburton's systems. So Halliburton is one of the major suppliers of control systems, so it's nice to just see a bit. You also saw the passive orientation system, where as they were lowering it down, it would rotate in order to get into the correct position. That is used for much equipment that needs to be oriented to a specific position. Then they often use these passive systems to orient them and lock them into place. So now we were at the multiplex one, I think. That was the electro-hydraulic. And then we are at the multiplex electro-hydraulic. Also be aware that this figure is actually simplified for the multiplex one, so it's actually even more complex than what's being shown here. But what we have is, we basically have a computer up here, where you can give your control inputs, you have your computer display, And then you have the CPU and everything doing what it's supposed to do when you're giving control inputs. Sends it into the modem, which sends it down to the control module down by the Christmas tree, which is usually located either on the Christmas tree or right next to it. So the only thing you need now is hydraulic pressure going down for one line, and then you have this one signal line going down. So that's all you need to keep up your controls here. And this signal line is most often an Ethernet cable, so it's basically an internet cable. So you're connecting it using not a wireless system, but a wired internet connection. And then you have a computer down here which receives the signals, interprets them, and then activates the different electronic valves that are supposed to be activated. It also receives input from all of the sensors that are down there. So pressure sensors, temperature sensors, and everything get input into this computer, and it sends the signals back up to the computer, and you get them shown on your display. So this is sort of considering the amount of technology that we every day surround ourselves with, this is what you would expect to be there. But you have to remember that the oil industry is fairly old. So at least in Norway, it started in the 70s. And it's very conservative. They really don't want to start using new stuff until it has really proven itself. But in order for new technology to prove itself, someone has to start using it, but nobody wants to use it because it needs to prove itself. So it's sort of a bad circle they have going there. But there's always one or two companies that are willing to try one new technology every now and then, and that's when you get these really good ones, like these multiplex. Once they get to show what they're worth, and when the rest of the company sees that, hey, this was really a good system, and it's also reliable. It might even be actually more reliable than the direct hydraulic stuff that we already have. And then they will want to use this new and reliable technology for their newer developments. But then often they don't upgrade their old ones, not unless they have to. If they need to upgrade the field because they have found new ways of getting more oil and gas from that field, then they might do some upgrades to the rig or the vessel. But usually they don't upgrade without having to upgrade. So we start off with the control system up top. We've got the hydraulic power unit, the HPU. We have the electronics to control it. We need an umbilical to go down to the seafloor. And then we have the Christmas tree, which is connected to the umbilical. And then we can see here beside this is the Christmas tree, and then beside the Christmas tree here is the control pod, where all of the electronics are being interpreted from the control valve and from the control panel up top, and then all of the different electronic valves are activated, which again activates the hydraulic valves inside the Christmas tree. So it's sort of there are many stages to this system. So you might think that it's a fairly complex system, since something could go wrong up here, something could go wrong in the umbilical, it could go wrong in here, or with this electronic valve, or with this valve. So there's a lot of points where you can have something go wrong, and I can sort of understand the oil industry where they are saying that, well, we don't want to just put this out there. It has to prove its worth first, that we know that it's actually reliable enough to be used. So I can sort of understand it, but sometimes they are a bit too conservative when it comes to this. So the control and monitoring signals. So the control signals to pulse-operated solenoids are sent from the control panel. And what are solenoids? I know Runal has talked a bit about it in the hydraulics part in one of his lectures. It is basically a regular hydraulic valve, but you have a long shaft on the valve, which is magnetic, and you also have a power supply and a coil of wire going around this shaft, which means that as soon as you send electricity through the coil, it's going to create a magnetic field here, and it's going to move the piston in the valve, which means that you are either going to open or close the valve, depending on the direction of the current that you're sending in there. And also the monitoring signals from the Christmas tree, they are sent through the control pod, which is called. Some companies call it a bottle, some call it a pod. Basically, it just means that it's a pressurized unit where you have atmospheric pressure inside with all of your electronics. So basically, you have air inside, breathable air, and then you can have quite a lot of pressure on the outside because the pod has enough strength to withstand the hydrostatic pressure of the ocean. Actually, what I said there, breathable air inside. Often they have atmospheric pressure inside, but it's not regular air. It might be pure nitrogen. I also know that some companies fill them with CO2. And this is basically in order to ensure that there's a pure gas inside. Because if they put in regular air and just let it fill with regular air at regular pressure and then close it off and then send it down there, the temperatures might make the moisture, the humidity in the air, might make it condense. And you don't want water around your electronics equipment. So then often they actually exchange the atmosphere in there for a different gas, because then they are sure that they have only one gas in there and there won't be any humidity. So that is very often done for subsea cameras as well, simply because if you have humidity in there and you have this viewport which the camera needs to see through, and if you got humidity in there and you get condensation on the inside, it's going to fog up and you're not going to see anything with your camera. So they also have to think about this when they're creating cameras. The monitoring signals that go through the control pod is, of course, the pressure and temperature of the Christmas tree. Leak detection, if you have any leak detection sensors down there to check if there are hydrocarbons leaking into the ocean. Downhole pressure and temperature, so sensors that are actually down inside the well, not just up on the Christmas tree. And you also have different so-called housekeeping parameters for watching your system and the operation of it. So you want to know your hydraulic supply, how much flow are you getting. I know usually you have a flow meter up top side by your pump and your unit, and then you also might have a flow meter down by the Christmas tree monitoring it, just to check that you're getting what you need, and also that you are having the functional pressure that you need down by the Christmas tree. It's nice to get in. That you have enough power getting down there. That's important. If you're going to operate these solenoid valves, you need enough electricity to run them. And for this next one, which is a conventional electro-hydraulic system with a subsea hydraulic pressure unit, HPU. So here we have the umbilicals going up to the platform way up here. Have you seen this symbol before? Where you've got this sort of inverted delta symbol on top of a squiggly line. So this means that this is the top of the fluid, in this case the ocean, and it means that you have atmospheric pressure on that side. So when this, you have regular atmospheric pressure on top of your water. That's just basically what it means. I'm pretty sure you had it in your fluid dynamics. But so as you can see, there's a lot of different stuff going on inside this control pod. We have the, let's see, it's even difficult to read here. Yeah, this top one, where you have a continuous line and then a dotted line, those are the supplies. So electrical power and signal, which is coming down from the platform. And then you have the electrical signal cables that continue on inside the system here. So they go on to the different valves that they're going to use. And the continuous lines, they are the hydraulic lines. So they are going into the system here through different types of valves in here, and then over to the larger valves that they're going to run. And some of these pods also have these sort of mechanical block schematics. But they're really, really awful to read. At least you can see the base here, the regular base that we see with the guiding systems to guide everything. We connect it down. This is just a pod. It's not the Christmas tree, not the entire Christmas tree. This is just to connect the control pod into it. And we have a lot of connectors in here, so that when we lower it down, it's going to be connected. And all of the different components are placed in here. We have some pressure compensators and everything going on here. So it's, as you can see, it's open to the ocean here, and it's got sort of a bellows or stuff in here, so that the water can get into the bottle, and then it will put pressure onto this bellow, which will also put pressure onto the hydraulic fluid that's inside it, so that you sort of get an equalization of the pressure. So you use the pressure of the seawater to equalize the pressure of the hydraulic system in here. Next one is a bit better to see. So this is a multi-well control system with its block schematics. So we have the different pods of the system here. The umbilical is coming in, connected to each of the pods. And here we have the tree cap up top and the Christmas tree over here, sort of just illustrated. So we put the entire control stuff on the side of the Christmas tree. So here's a isometric view of the control module. We have the guiding points down here, the connectors up top here. So we lock it into place, and then we get connections. And this one is also difficult to see, but these are the main components of a subsea control system. So here's where we lock it onto the template, and here we have the main components inside. So you can see the bottle or the pod, it's pretty filled up with equipment, so it's jammed full here. And you've got more like the computer stuff up top there. And these are, the valves and other stuff going on. So let's see. Yeah, and then we'll look more at the hydraulic system for the control of subsea wells. So there's a bit more to look at here. You can use open circuits where you are returning the fluid, the exhausted fluid to sea. So you're just basically, you have a valve down by your Christmas tree. So you're pushing your fluid down to operate the different valves, And when you're done with the fluid, you just release it into the sea. But then, of course, you're not using hydraulic oil to use this. You're usually using a water glycol emulsion. And then you have the closed circuits where you're returning the fluid back to your hydraulic pressure unit. And then you are usually using regular hydraulic oils for it. Usually we're using one low pressure supply, around 210 bars. And this one goes for the different functions on the Christmas tree and the manifold. And then you have a high pressure supply from 345 to 690 bars. And it goes to the surface controlled subsurface safety valve. So you want a lot of pressure there in order to keep this valve open. Remember, this is one of those fail-safe valves, so if you actually lose this pressure to the valve, it's going to close. And then you have to reapply the pressure in order to open the valve. So the next one was... Yeah, this is sort of a schematic of the pilot-operated Poppet valve. So here's the valve itself, the Poppet valve. We'll be getting more into the different hydraulic valves as we go along in the hydraulic systems part. So I'm not going to go too closely into this one right now. But the point is that you have the solenoid valve, which is controlling this valve. So the main hydraulic pressure is going through this valve, and this valve is being operated by the solenoid valves. So that you get you can use quite a small amount of power to operate these valves because they are very small, but they are strong enough to move the slide inside the main hydraulic valve. And when this slide has been moved, then you get the hydraulic pressure flow into wherever it is you need it to go. Yeah? Yeah, we'll do a break. Right. I know that the stuff we're going through now, it's quite difficult to sort of comprehend everything. But just keep in mind that for the exam, this appendix, it will still be relevant for the exam, but I won't be going into details on any of my questions. So it won't be like, how many bars of pressure can you expect this and that valve to operate at? What you need to know is like, what kinds of different Christmas trees are there. There are vertical, there are horizontal, and those different kinds. You will also be allowed to bring the book, so you can actually look it up while you're there. But it's sort of the big picture stuff from Appendix A that's important for the exam. So just basically how these subsea systems operate in general, not the really small details and stuff. So that's also why I'm going fairly quickly through this control system, because now we're getting into a lot of details here. So we will be looking very into detail onto valves when we are getting into the hydraulic systems part. Further into that, we are going to be looking at most kinds of valves and how they operate and how they are built and everything. So we will be getting into that as we go along. So that's why it's sort of quick and difficult to get it right now, but it will be easier on the exam. It won't be necessary to know all the details, basically. So for direct acting valves, which means that you get the hydraulic pressure from What was the question? Yeah, you're going to have the submission that's coming when we get to part 3. I can't remember which week it was. Yeah, at the end of this month, I will be releasing a submission, and then you have well over a month. You have almost 5 weeks to do the submission. Yeah, but that's what I'm trying to say. The submission that you're going to deliver later on is going to be fairly close to what an exam is going to look like. And you will get 5 weeks to work on it and look at it. But it's going to give you the insights into what kinds of questions am I going to ask in the exam. Because there will be a little bit of calculations concerning ROVs and diving, which we will get to in part 3 and 4. So that's why we are waiting with this submission until we get to those parts, basically. But mostly it will be theoretical questions. So explain this or explain that. And then you answer those questions as much as you can, basically. Right, so back to the direct acting valves. So direct acting valves, they are the ones that we use in the direct hydraulic control system. So they get their signals through. They have their own hydraulic supply to every one of them. So it's a very low complexity, as we saw at the start. You have quite a lot of hydraulic connections, but you don't have many places where it can go wrong. You don't have a computer that could go something wrong with, and then an umbilical, and then a control module with a computer in it that could go wrong, and then electrical piloting valves, and then the main valves. Here you will just have the valve on top, on the top side, on the rig. You will have the umbilical, and then you will have the main valve. That's everything that can go wrong in a system like this. So it's very low on complexity, which means that it is fairly reliable. You will know right away if something is wrong with the system, because if one valve doesn't react, it has to be either the valve, the umbilical, or the control panel up top. So it's sort of very easy to find the errors in it, and fairly easy to fix it also, so long as it's not inside the umbilical somewhere. But you get a limited flow capacity for a given power consumption. So you are limited on your flow capacity through the system. So you will get increased pressure ratings, will increase how much power you need to use. Either that or it will reduce your flow capacity. You get acceptable enough values for flow capacity, pressure rating. In order to get acceptable values for flow capacity, pressure rating, and power consumption, it limits your design solutions because there are quite few solutions that give you acceptable values for all three. So then you're stuck with that design. You can't really be creative and create a whole new solution because the fluid dynamics and everything just puts on the brakes and tells you that, well, you can only do this in a couple of ways, and that's the only ways you can do it. And generally, you have smaller design margins, so that you can't really expand the system very much. And also, as I noted in the start, you get very large physical dimensions. The umbilicals are huge for this because you have so many different hydraulic connections going through the umbilical. And then you have the pilot-operated ones, whether they are pilot-operated hydraulic valves or if they are the solenoid electronically operated pilot valves. Doesn't really matter as long as they are pilot-operated. You get a high degree of complexity for the system because now you have, yeah? That there is no umbilical. Yeah, well, the umbilical is still there. It's just that it's instead of having signals going through it, it's having the direct pressure going to every single valve. So instead of having one thick connection which is delivering all of the pressure, which is then getting distributed, then it's getting loads of smaller connections that are delivering, every single one of them are delivering pressure to the different components. Which means that if you're going to have a great flow capacity with great power, which gives you a lot of power without having to use much of it, and high pressure, you are going to need to have quite a huge dimension on every single one of these hydraulic connectors that are going inside the umbilical. Which means that the umbilical will be very large, so you get large physical dimensions for it. So for the pilot-operated ones, we have a high complexity, which is negative, because there's many more steps that can go wrong along the way. But we need a very low flow capacity in order to operate the pilot valves, which allows us to run a high pressure and high flow capacity through the main supply, and then we run a low flow capacity in order to operate the different valves, while the high flow and pressure rating goes through the valves that it's supposed to go through, instead of being used well, let me rephrase that. You can direct the entire high pressure, high flow capacity supply into one valve instead of having it distributed to all of the valves like in a direct system. So here you are using a very low flow capacity to tell the pilot valves direct everything from the high pressure, high flow capacity supply into this one valve, so that you get a lot of you basically get a more efficient use of your power supply here. And generally large design margins, so it's easy to expand systems like this. And they have small physical dimensions because the low flow capacity means that you really don't need very large hoses in order to inside your umbilical in order to deliver the pilot signals to these pilot-operated valves. So one of the ways they can be connected is that you have the the solenoid part. Actually, for the symbols, so this is one of the standard symbols for a valve. It means that if we connect something to, I'll just draw it here instead. I think that's easier. So this one was so what this one means, the center part here, is that we connect a hydraulic line here, we connect a hydraulic line here, and we connect a hydraulic line here. So usually, when this one is being operated, the flow will go from this side, and it will go through here. So it's not a problem. But if you operate it, it's going to switch. So let's see, I'm going to do this in red, try to differentiate this a bit. It's going to push the entire valve over here. The lines will still stay in the same place. But now the insides of the valve have been moved. Which means that when you are using this valve regularly, it will go through the black here. But then if you activate it, it will be pushed over. And then this line is what's going to be connecting. So the flow will go from this side and up here instead. So that's what these symbols mean. But these are, we're going to go very thoroughly through these in the hydraulic system. And the edge, the tip here, that's symbolizing the solenoid control of it. And this part here means that it's spring operated also, so that unless you are giving it an electric signal to push it over, then it's going to be pushed back by the spring afterwards. So if you cut the electric signal, it's going to be pushed back. And this one is just to show how you can build in redundancy, I think it is. The part was, or was it? See, it is. Yeah, this one is for redundancy. So you have the coil, and then you have a circuit A, which is coiled in here, but you also have a circuit B, which is also coiled in here, which means that basically you have two different coils that you can use, so that if you usually use your circuit A to put your electric power in here and activate it, if that circuit is broken somehow, wear and tear over time, it might lead to a break somewhere inside, maybe inside the coil or maybe inside the connections here somewhere. Then you won't get power flowing through it anymore. But then you can just switch and use circuit B, because that's on a separate coil, which is also the same build-up in this system, just showing another way of setting it up. So it means that you have one system which you use regularly, and if that fails, then you start using the other system, which gives you a lot of leeway with regards to not having to think about exchanging the valve until the first system sort of stops working. Then you need to think about, well, now we only have one working part on this valve, so we have to schedule for the next scheduled maintenance. We have to exchange this valve, but it's still working until your next maintenance. So you have the shuttle valves, which you can use to direct flows in different directions. Again, we're going more into detail on this when we are getting into the further into the hydraulic systems. Now we'll look a bit at the umbilicals. So you can have the flat kind, where you have stainless steel tubes going through the center here, and then you have strength members, basically just steel wires, out on the edges. Those are mainly there just to give strength to the umbilical. And then it's through the steel tubes that we are delivering our hydraulic pressure or signals. And then you have the hydraulic umbilical with a synthetic hose, which is no, this was the next one from the top on the figure. They're all in one line on the figure instead of being beside each other. So we have the composite umbilical, where you have a communication conductor in the center. You have hydraulic hoses, these white ones in the center. And then you have power conductors here. Then you have a strengthening layer going around here. And then all the way on the outside you have a jacket. And the jacket is like the rubber coating of it, just to give it some protection. And then you have the sort of steel wiring, like you saw on the flexible pipelines, where they are putting it in different directions, or sort of spiraling it in different directions, just to give it more strength. That's kind of what they're doing here also, creating basically a hollow steel wire. And then inside the wire they're putting all of this. So here we have the power conductors, and also we have communication conductors. So the communication conductors are only sending signals. So they are sending ones and zeros along the system, while the power conductors are sending voltage through it. So they are sending electric current, and then the hydraulic hoses are, of course, sending hydraulic fluid. This one is a purely hydraulic umbilical. So it has basically the same design as this composite umbilical, where it has the armor layer and a jacket outside of that, but it has only hydraulic hoses inside. It doesn't have the electrical wiring. And here we have a pure electrical umbilical. Again, the same stuff with the armoring layer and then the jacket around, and then you have power and signal cables inside. Yeah? This one? Yeah. Yeah, they send the electric power through it. Those are sending hydraulic fluid, yeah. Yeah, basically, they are basically, both of them are sending a power supply down. So it's a hydraulic power supply and it's a electric power supply down. So both of them are sending that. But if you have a large system, like the multiplex one, you need the communication part. So you need to send down the signals in order to tell the control module what it's going to do. But then you also need electric power for the control module so that it can activate the electronically operated solenoid valves inside the control pod, which again directs the hydraulic fluid into the correct valve in the subsea tree. So that's why you need all three of them, basically. Here we see a really huge crab, as you can see. I'm not quite sure why they put that big of a crab down there, but maybe just to signify that this is the ocean floor. Here's a basic build-up for an umbilical going down. You have these buoyancy elements that lift it up from the ocean floor, which gives the ability of having quite a large amount of flexibility here, because this vessel is going to rise and sink with the tides. It's going to move up and down with the waves and everything. If all goes well with its dynamic positioning systems, it's going to stay in place, so it's not going to drift around, but it will be moving up and down a lot. Even in calm weathers with fairly flat seas, you still have the tides moving the water up and down, so that it's going to move up and down anyway, and that's why you want this sort of S bend to the umbilical, because this means that the umbilical has a lot of leeway to move. Because if you had gone directly from here and in a direct line up to the vessel, you could risk that when the vessel was moving upwards, it would start straining on the entire cable. So you could risk that you would either snap it somewhere along the line, or that you would yank it out of its connectors or something. So you don't want that. You want to have a lot of room to go on here. Basically the same as if you're sitting down with your laptop and you have it plugged into a wall socket. You want to be fairly close to the wall socket so that you have a lot of wire to go on if someone comes walking there and they stumble on your cable. You don't want them to pull that it's going to be pulled straight out of the wall. You want it to be just moved a bit, and then you can move it back afterwards. And here you have the same. You have a lot of different. Here's a lot of different stuff going through it, so it's a very complex umbilical. But you have electricals, you have hydraulics. I don't have the legend for this one. I think. No, I don't have the legend for it, so I don't know what each of these symbols are meant to represent. But here you have actually a picture of the same kind of umbilical. So you can see more how it looks like in real life. So here you see you have green, blue, red, and green wires going through it, electrical wires. This looks like hydraulic tubes. And there's probably, this could be the flow line in the center, actually. I'm not quite sure on that one. But this is a dynamic umbilical, so you get a lot of movement on it. So you have PVC around the center pipe here. Yeah, and you have the PVC going around it to protect it. And in order to connect these electrical wires when they are getting down on the subsea floor, you need to connect them somehow. But you can't use, like we're using here, a wall socket. That would mean that water would penetrate into the wall socket, and then you would short circuit everything. So you would get a complete blackout of everything. So they had to figure out different ways of connecting stuff. So what they've done is, I'm not sure if any of you have an electric toothbrush. So if any of you have an electric toothbrush, you will notice that you can just place it on top of your charger, and it's going to charge. You don't have to connect it in any way, so you just place it on top. The same with a charging plate for newer smartphones. Some of them also have this wireless charging. It's the same principle that they are using, which is basically that they have an electric coil where they are sending power through the coil. They are creating these magnetic fields, and then you have a receiving coil. This coil doesn't have any power going through it, but as these magnetic fields from the charged coil reaches it and moves through it, it is generating electricity on this side, which means that you can basically move electricity without actually being into contact with each other, and without the risk of having water contacting them and short-circuiting everything. It's the same that happens if on your oven stove, on your stove in, not your stove, but your oven in the kitchen. If you have induction plates, it's the exact same thing that happens there. So it's transmitting it through these coils, and it's creating magnetic fields that are heating your cooking pots, basically. So that's why only a certain kind of cooking pots work on an induction oven. It's because it needs to be magnetic, or else it's not going to be heated by the induction plates. So if you put a ceramic kettle or something on top of an induction plate, nothing's going to happen, because there won't be any heat or electricity running through it. So that's how they do these connections. But you do get a lot of power loss through it, so that it's not a perfect system. But I know that there's a lot of these companies that are delivering these kinds of solutions for subsea use. They are really working hard in order to improve them. They want them to be as good as possible, and they also want to improve them to the point where they can do signal transfer, so that they can come down from the vessel down into the coil with signals like down through an Ethernet cable maybe, and into a small computer here that will just interpret the signals, and it will generate pulses that will create ones and zeros on this side that will go into the electronic system, because then you suddenly have a plug-and-play system where you can just come down with a wire and you can plug it into your Christmas tree, and then you're connected. You can tell the Christmas tree what it's going to do. So that's what they are working on heavily now. This was just a nice one to get a feel. Here they are creating a subsea electric motor. So this is a company in the Stavanger region. Actually working in Inventor, as you can see. Here they are winding the coils that they're going to use inside. They put it into a module that they're going to put subsea. Actually see the module being lowered into the sea. So as you just saw, it's actually possible to put entire electrical motors down. down to the on your system subsea, and that is what they are doing much in the newer development when they're developing new fields, where they are actually thinking about putting a lot of the processing equipment down on the seafloor. Then they will need a lot of electric motors and stuff to run things. So it's really important that they have equipment that will work down there. So we are now at figure 8.18, which is just to show a bit that you can use different control systems when you're doing workover, which is basically when you're doing maintenance on the Christmas tree. So you often will connect a different control system then, and you will control everything from that one instead. That's just a quick presentation of the arrangement. So here's the rig floor. So you have everything above here is on the rig, and there's the sea level, and everything down here is the Christmas tree. So here we have a safety block up top in order to make sure that everything will run okay. We have the hydraulic pump, is it? No, that's a methanol pump. We have a pressure pack with different valves, a manifold and everything. We go down into the subsea tree, and here they can control everything down here. Here's a schematic of it. So you really have to keep your wits about you if you're going to start doing work on something like this. And this is the control schematic for a running tool that you're going to use for it. So the different kinds of tools that you will use in a workover. So a tubing hanger running tool. So the running tools are the ones that you're lowering down from the surface, and then they do some work for you down there. So the Xmas tree and tree cap running tool are the ones that actually bring the Christmas tree down and place it, and then they go up again. And if you need to pull the Christmas tree up at a later point, maybe you need to do an overhaul of the Christmas tree, or maybe you need to exchange it, then you will use the running tool to go down and pick up the Christmas tree and pull it up. Guideline establishment tools, flow line, umbilical, pull-in tools, and connection tools. So the pull-ins will be just to be able to pull these lines into the correct position, and then you will have a tool that will connect them. Some of these tools are sort of 2-in-1, where you can also pull in and then connect, so that you don't need to exchange tools in the middle of it. Control module running tool, choke module running tool, pig launchers, subsea. If you need to go down to a manifold or something and you're going to run a pig through the lines, then you might not be able to run the pig from shore and out to the well. Then you will have to go down to the subsea area and launch the pig from there. And the subsea lubricator with this stuff box on top when you're doing wireline operations. And then if you're going to insert valves into the Christmas tree, so if you're going to exchange a specific valve, then you have a different tool for that. Yeah, these are different routes that you can take in order to have control. So control functions can be routed through the Christmas tree cap in the production model. So you can send everything through the cap of the Christmas tree, basically. So you come in from top side, you go into the control pod, and this sends it through the tree cap and then into the tree. Then you can put it into workover mode, where you send it in through the top. So now you've disconnected you've disconnected the tree cap, so this control pod doesn't have any connections anymore, and you are coming down with an umbilical through the top of the tree instead in order to control it. Instead of doing it through the tree cap, you can have a cap on top of the control pod so that you route it down into the control pod instead. So when you disconnect the cap, you also disconnect the two different sides of the control pod, and then you can come down and sort of overrule the control pod there. Because if I'm not quite mistaken here, the control systems that you have topside are to some extent automated. So it will start doing stuff when it gets signals from its sensors, like too much pressure in the annulus, it will bleed off the annulus automatically and stuff like that. So it's nice to actually disconnect it to be completely sure that the regular control system won't interfere when you're doing the workover. So then you want to completely disconnect it so that you know that you have full control with the workover control system. And there are some safety features you want on your not your emergency, but on your workover control system. You want to have an ESD, an emergency shutdown function on it. And you also want to have an emergency quick disconnect, especially if you're coming in with a different vessel and you are connecting to it. If then suddenly the weather worsens, especially out in the North Sea, in the North Sea, the weather can change from being calm seas to almost a storm in just a couple of hours. So you can actually be surprised by the weather out there. So that you will have to do an emergency quick disconnect. And then you also want it to be explosion proof, of course. So you want to avoid explosions when you're out there. And then for a direct hydraulic workover system, you need to have your HPU, which is the hydraulic pressure unit, which is basically just the motor and the pump of the system. We'll be talking more about that in the hydraulic systems lecture tomorrow, actually. Tomorrow or on Friday, can't quite remember right now. You need a main panel for controlling it. You need a drill floor panel. So the main panel can be situated inside a control room, but you also want a panel out on the drill floor of the rig so that you have something very close to where the workers are, so that they have the possibilities of doing an emergency shutdown. If they notice that something is wrong here, we have vibrations or anything, then we're just going to shut down the system. They don't have to run into the control room and shut down the system. So then they have their own buttons to push. And you have separate emergency shutdown remote panels on different locations, so in strategic locations, so that they can do a shutdown if needed. You will need a heavy umbilical reel if you have complex tools, and you need a light umbilical reel if you're just going to do tubing hanger running tools and the more lighter tools that you're going down. You need hydraulic, pneumatic, electric jumper cables of different sorts. And then you have the lower riser package, the LRP, with its control valves and accumulators. So that's the part that you connect on top of the Christmas tree when you're going to do the workover. Then we have something on surface equipment. Let's see here. Yeah. The heavy umbilical reel is for the heavy equipment, such as the lower riser package and everything that has a lot of weight that you're going to lower down. It needs its own umbilical reel for it, while the lighter tools can be done with a light umbilical reel, so that you don't need to pull out this huge reel of umbilical to do the light stuff. You can use some lighter equipment, basically. So it's mainly to conserve a bit of power, because the light umbilical reel is much easier to run. So it's not that heavy for the system, so you don't need that much power to run it. And it's a bit easier to move around and do work with. So for the surface equipment, I don't think I have any points there, but you will need something that generates power, a power generation plant. You need your control panels, and if you're going through a flow line, you will need pumps and tanks in order to do that stuff. And often there are both space and load, as in weight, requirements to the equipment, because you have limited space on deck. So the actual footprints, the square meters of each of the equipments is quite limited. So you have to make sure that you can fit all of the equipment that you're going to use on top of the deck of the vessel you're using. And also the weight, of course, because if you have really heavy equipment that you're putting on top there, you might have to go into like a bill here or something, and they might have to weld on supports on your deck just to make the deck stronger in order to take all of this weight. Because if you're going in with if you have a vessel and you're going to load up 4 BOPs on it, and each of the BOPs weigh 250 tons, then the regular deck of the vessel won't be strong enough to handle that, so you're going to have to weld in more beams and stuff to make it stronger. I think we'll stop there for today. So we'll do installation, which is chapter 10, on Thursday. And on Thursday we will definitely be finished with Appendix A. So then we will move on to the other appendixes here. Yeah, what was the question? What did you say? Chapter 7, what was that? That was... just have to check what it was. So chapter 7, that was the... yeah, that was the wireline and through flow line stuff. So that was what we started with. We did a little bit of it last week on Thursday, and then I did the rest when we started today. But it wasn't really much. So